It's 1975, and in a quiet office in Palo Alto, a researcher sits down at what looks like a piece of office furniture. Under the desk is a beige cabinet the size of a small refrigerator. On top, a tall, paper-shaped screen, a keyboard, and a strange little box with three buttons, a mouse. The researcher moves the mouse. A tiny arrow glides across the screen. He clicks to bring one window to the front, covering another. In one, an email program, messages from colleagues around the building. In another, a word processor where bold headings and italic footnotes appear exactly as they will on paper. Nearby, a laser printer, also experimental, waits to turn those pixels into crisp black ink. He edits a paragraph, drags a diagram into place, and sends the finished document across the network to a shared printer, all in a few minutes. No punch cards, no operator in a distant machine room, no overnight turnaround. Just a person, alone with a powerful machine, shaping information on a screen. This scene took place a decade before the Macintosh, years before the Apple II, before personal computer was a phrase most people had ever heard. The machine was called the Xerox Alto. Inside Xerox's Palo Alto Research Center, PARC, hundreds of these systems quietly sketched out the outlines of our modern computing world. Graphical displays, point-and-click, Ethernet networking, laser printing, and more. Yet Xerox would never sell the Alto as a product. The company that built the future treated it as an experiment and let others turn its ideas into an industry. To understand how radical the Alto was, we have to go back to the late 1960s and early 1970s, when computers were big, rare, and distant. In most organizations, computing meant mainframes like IBM's System 360. These were room-sized machines, tended by specialists, fed by stacks of punched cards or reels of tape. Users prepared their programs or data offline, handed them over, and waited, sometimes hours, sometimes days, for printed results to come back. Even with newer mini-computers, like Digital Equipment Corporation's PDP series, the pattern was similar. A single machine time-shared among dozens of people reached through text-only terminals. You typed commands and lines of code into a green or amber screen, one fixed with character after another. If you mistyped a command, the computer simply rejected it. The assumption was clear. Humans should learn the machine's language and rhythms, not the other way around. There were hints of a different path. At SRI in Menlo Park, Douglas Engelbart's team had built the ON-line system, NLS, which in 1968 he demonstrated in a famous hour-long presentation, later nicknamed the mother of all demos. Engelbart showed a mouse, hyperlinked text, video conferencing, and collaborative editing. It was visionary, but it remained an exotic, one-of-a-kind research system. At the University of Illinois, the Plato system experimented with graphical terminals, online lessons, and even early message boards and games. Plato hinted that computers could be social, interactive, and visual. NLS and Plato together formed part of the intellectual soil from which the Alto would grow. The idea that computing could be direct, interactive, and centered on the user sitting at a screen. In 1970, Xerox decided it needed a foothold in this emerging world of computing and information. Rather than just buy more mainframes, the company created a new research center on the outskirts of Stanford University. The Palo Alto Research Center, or PARC. PARC was unusual. Xerox gave its new lab generous funding and remarkable freedom. Researchers were encouraged to think a decade ahead, not about next year's product catalog. Out of this environment came a bold idea for a personal, portable computer, the Dynabook. The Dynabook was the brainchild of computer scientist Alan Kay. In a 1972 paper, he described a personal computer for children of all ages. A book-sized device with a screen, keyboard, and network connection that a child could carry anywhere. It would let users read, write, draw, simulate, and learn, all on a machine that responded instantly. The hardware to build a true Dynabook didn't exist yet. But Kay's colleagues believed they could build something close in spirit, with then-current technology, a powerful personal machine on every researcher's desk. They called it the Interim Dynabook. In 1972, Butler Lampson wrote a memo titled "Why Alto?" laying out a plan for this new system. It would be a small but capable machine for a single user, with high-resolution graphics and a local network. As Lamson put it, if our theories about the utility of cheap, powerful personal computers are correct, we should be able to demonstrate them convincingly on Alto. Under the leadership of Bob Taylor, who had previously managed the computer research program at ARPA, a team formed to make this real. Charles "Chuck" Thacker led the hardware design. Alan Kay pushed for the Dynabook vision. Lamson and others worked on the system's architecture and software. Meanwhile, Xerox's Special Programs Group in El Segundo, California, with Doug Stewart, Abby Silverstone, Bob Nishimura, and John Ellenby, handled the practical job of turning a lab prototype into something that could be manufactured by the hundreds. The result would not be a tiny battery-powered tablet. It would be a desk-sized machine, but for the people who used it, the Alto would feel far more personal than any computer before. Seen from the outside, the Alto was almost modest. A beige cabinet, a tall monochrome screen, a keyboard, and a small 3-button mouse. Its appearance gave few clues to how unusual it was. The cabinet, about the size of a small refrigerator, held a custom-built 16-bit computer. This was not a microprocessor system. General-purpose microchips were still primitive in 1973. Instead, engineer Chuck Thacker and his team built the Alto's central processor from many individual logic chips called TTL, the same building blocks used in many computers of the day. At its heart was an arithmetic unit built from 4 Texas Instruments 74181 chips, then a standard way to construct a fast, flexible calculator inside a machine. The Alto ran at about 5.9 MHz and used a technique called microcoding. Instead of having all of its basic instructions fixed in silicon, it stored many of them in a special control memory that programmers could modify. For certain applications, graphics for example, this meant you could add new, very fast operations that worked almost like built-in hardware. The first Altos typically shipped with 128 kilobytes of main memory, later expandable to 512 kilobytes. By modern standards, that's tiny, but in the early 1970s it was substantial. A significant fraction of that memory, nearly half in early configurations, was devoted to the display. Mass storage came from a removable disk cartridge made by Diablo Systems, holding about 2.5 megabytes. Each user had their own disk pack, which you could slide into the front of the Alto like a thick plastic record. The most striking feature, though, was the display. Instead of the common landscape-shaped monitors of later decades, the Alto had a tall, portrait-oriented screen, 606 by 808 pixels. It was bitmapped, meaning each tiny dot on the screen was represented directly by a bit in memory. That allowed the system to draw arbitrary shapes, multiple fonts, and complex page layouts, anything you could describe in software. For input, the Alto used a standard keyboard, a 3-button mouse, and, for some experiments, a 5-key chording keyboard. By pressing combinations of those 5 keys, a user could type characters without moving their hands. The chording keyboard never became mainstream, but the mouse would. Inside Xerox, each Alto reportedly cost on the order of $12,000 in parts to build. If sold commercially at normal margins, contemporary estimates put a price tag in the $30,000 to $40,000 range, well over $100,000 in today's money. It was never going to be a consumer product. But as a research platform, it was unmatched. The Alto's hardware made one crucial thing possible, a new kind of relationship between humans and computers, built around graphics, windows, and direct manipulation, instead of lines of text. Unlike the text-only terminals that dominated the era, the Alto could draw detailed images anywhere on its screen. The operating environment, called the executive, initially greeted users with a command prompt. But on top of that, PARC's programmers layered a growing collection of graphical programs that took full advantage of the bitmapped display and mouse. One of the most important was Bravo, a word processor created by Charles Simonyi and his colleagues. Bravo was the first widely recognized WYSIWYG text editor. What you see is what you get. That phrase meant something very specific. When you looked at a document in Bravo, the fonts, margins, and line breaks on the screen matched what would come out of a laser printer down the hall. Before this, word processing usually meant typing plain text and inserting hidden formatting codes, then hoping the printed result was correct. Another key application was Draw, a graphics program that let users create diagrams using the mouse to select commands from on-screen menus and manipulate shapes directly. For engineers and designers at PARC, this made the computer a practical drawing tool, not just a calculator. The Alto also supported early email and file transfer programs, letting researchers send messages and share data across an experimental local network. That network, called Ethernet, was developed at PARC to link Altos and servers together over coaxial cable. It provided a fast, shared connection to resources like file servers and, crucially, to high-quality laser printers. For the first time, an office could have multiple personal workstations, all talking to the same digital printer. The machine was also a hotbed for new programming ideas. Alan Kay's group developed Smalltalk on the Alto, one of the first fully object-oriented programming languages. In Smalltalk, everything on screen, windows, buttons, documents, was an object sending messages to other objects, a style that would later shape languages like Java and C. Another language, Mesa, was created at PARC for systems programming and would underpin later workstation projects. Not everything on the Alto was serious. Researchers built networked games such as Maze War, a first-person 3D maze you could wander with other players over Ethernet, and Alto Trek, a Star Trek-themed game. These experiments showed that once you had graphics, networking, and a personal machine, new forms of play and social interaction followed naturally. For all its ambition, the Alto remained officially a research system, not a commercial product. Xerox never put it in a catalog or shipped it through normal sales channels. Instead, the machines quietly spread through internal and academic networks. After a pilot run in the early 1970s, Xerox approved larger production. Over the rest of the decade, roughly 2,000 Altos were built. By the late 1970s, about 1,000 were in daily use inside Xerox, especially at PARC and related labs. Another 500 or so went to universities and research institutions, often as donations or on favorable terms. These external Altos helped spread the system's influence. Computer science departments used them for advanced courses, graphics research, and networking experiments. Students and visiting researchers carried the ideas they encountered on the Alto, bitmapped windows, mouse interaction, email, and Ethernet, back to their own projects and, eventually, companies. A small but symbolically important cluster of Altos even made its way into the U.S. federal government. In the late 1970s, word processing systems based on Alto technology were installed in parts of the White House and in congressional offices. Staff could draft and edit documents on screen and print them with laser printers, foreshadowing the computerized bureaucracy that would become commonplace decades later. Because the Alto was never sold as a normal product, Xerox often treated it as a tool to be given away rather than a revenue source. Inside the company, thousands of employees used Altos every day, sending messages, editing documents, and printing reports. For them, the future of office computing had already arrived. But outside those walls, few people had any idea such a system existed. In that gap between internal practice and external perception lay the seeds of Xerox's missed opportunity. The company had, in effect, built a time machine and placed it on the desks of its own staff, while the rest of the world was still feeding punch cards into mainframes.